that is equal to, you can say 3.3 multiplied by 10 raised to minus 5. Incidentally, if you are using Excel for calculations like this, you have to make sure you use use it carefully. If you in Excel, if you say x, I guess this is just a computational thing. X multiplied by y and divide. So what's the sign for divide? Divide by z. No, I guess I wanted to say this. X divided by y multiplied by z. What will this do? Is this the same thing as this? In Excel, it's different, right? So you have to make sure that you do it correctly. So if that's what you wanted, you should better have the parentheses here. Okay. Okay, let's look at another example, sort of a continuation. Okay, compute mission time. We want to get mission time, and it is given that the threshold reliability is equal to 0.95. So basically what we are saying is that we need to figure out is to the value of Tm such that this is equal to 0.95. Basically you need to solve for Tm, and you can easily solve for Tm. Take log of both sides and you get natural log of 0.95 divided by lambda, and that is approximately 0.051 divided by lambda. Questions on this? So remember, whenever you go from power to something like this, typically you have to take log of both sides and do some rearranging. And continuing the example, here's another one. Now let us assume that lambda is equal to 3.33 multiplied by 10 raised to minus 5. Oh, I forgot to say here, per hour. Actually, it's very important to have the right units, especially when people are switching between hours and seconds. Seconds is sometimes a natural unit of time, but a lot of time people do it in hours or even other units. So I should have said that here. In fact, if in a test, if I ask, calculate this and give me the answer in per hour, then you have to have the answer in per hour. Okay. Find the mission time. Okay, so I plug in the value for the value of lambda here, and it turns out that Tm is equal to 1538.8 hours, if my calculation is right. Okay, so the mission time is about 1500 hours. Does it look reasonable kind of number, is it consistent with, let us say, this unit here, MTTF equal to 30,000 hours? Same thing. So notice that MTTF is a much looser measure, whereas mission time is a much strict measure. So your mission time goes up to until when the reliability drops to the threshold, and the threshold we had seen was 95%. 0.95 is 95%. And so mission time is much more strict measure. Any questions or comments on this? Okay, now let us look at a single unit with temporary failures. Now, when we say temporary, it could be, it's basically a failure that arrives and then it goes, and arrives and goes. So it could include intermittent. It could include the transient case and permanent with repair. Provided you assume that the repair process is also a stochastic process. Intermittent and transient, sometimes people use them interchangeably. Sometimes people make a distinction. Sometimes people say that intermittent failure is something because of a marginal unit. So you have maybe some electronic thing with some loose connections, and whenever there are vibrations, it has some intermittent failures. Transient is something because of environmental phenomena. So there is some electronic noise, or you have the, what is that called? Solar spot activity or some such thing, which is basically environmental. Sometimes people refer to that as a transient thing. But it can be hard to make a distinction between the two sometimes. But they are all included in this thing. And basically, we can view the behavior as being sometimes good and sometimes bad. And let's see, let's show it here. Let's say, should we make good on the top or bad? It doesn't matter. So basically, the system is good this time and sometimes goes bad. Then so here, basically, we have a temporary failure. So it goes between good and bad. So here is good, and here is bad state. So basically, you go from good to bad, but then there is the repair process that brings you back to good. And let us assume that it is controlled by parameter mu. Now to analyze this, we are using the same approach. And notice that this is the general approach for analyzing Markov processes. So this is we are assuming this is a Markov process. That means there is no the process is memoryless. If the system is here, there's a certain probability that in time delta t it is going to be here, but it does not matter how long you have been here or how long you had been here before, none of that matters. The process is memoryless. So, and we can describe this by a pair of differential equations. So notice that the rate of change of probability of being here includes two factors. So there is some probability going away. So that's the negative term there. Minus lambda times probability of being here. And there's some probability coming in. So probability of being here multiplied by mu. And for this, we have this. So this is the stuff coming in, and the stuff going out is this. So basically, we want to solve this system of differential equations subject to the condition that P0 is 0 is equal to 1. So that's the initial condition. Okay, what is the best way to solve this differential equation?
For the first line, it's minus lambda, the probability of P plus.
Let's see here. Oh, this one?
Yeah.
Minus lambda times P0t plus mu multiplied by P1t. So this is the probability leaving that state, and this is the probability arriving into that state, right? So you can think of probability as some, let us say, a liquid. So here you have certain amount of liquid, total amount of liquid is 1, and then the liquid is flowing. So wherever it flows, you have a higher probability. How many of you have been involved in solving differential equations? Okay, so I guess, oh, you have all done. Okay, that's good. Sometimes in so we have this online class. And in online class, we actually get students with somewhat different backgrounds, and sometimes they have to. They say that, oh, I took this stuff many years ago, so so I have to refresh my memory about what this is. Okay, so you can solve it. Okay, since you have all solved differential equations, how would you solve it? So what's the approach?
Using the MATLAB.
Well, there are, of course, automated tools available. How many of you have used MATLAB? That's a nice tool. So incidentally, I was wondering about MATLAB. So engineers, don't you use MATLAB?
Depending on what you're doing in your research.
Oh, okay. So is there a license for MATLAB for?
We have it installed on the
Okay.
server. On the
So
CS
what if you
server.
want to install a copy on your home
It's
PC?
licensed. You have to buy a license for it.
Oh, you have to buy a
I
license.
think, yeah.
Oh, so it's not, okay, I see. I know, I was checking the web for something. So somebody is trying to come up with a version of MATLAB which is in public domain. So, but it probably doesn't, they haven't built in all the capabilities, but it is modeled closely after MATLAB. Anyway, so, now let's assume you don't have MATLAB. So how will you solve it? And so there are a couple of ways you can eliminate one of the variables,